So, good morning. In this section, we will see few problems. So, first one is solve Laplace equation for the potential in the homogeneous region between two concentric conducting spheres with radii A and B, where B is greater than A. If V is equal to 0 at R is equal to B and V is equal to V0 at R is equal to E. So here you are coming across a new term, homogeneous. It means a medium having uniform property throughout its volume. That's all. Okay. Now before going to the solution, you have to by heart this equation, that is, you know what is Poisson's equation? Del square V is equal to rho V by epsilon. And Laplace equation is a special case of Poisson's equation, that is del square V is equal to 0. Then you have to by heart these three expressions, that is the Laplace equation for spherical coordinate, that is given here. Similarly, Laplace equation of cylindrical coordinate and Cartesian coordinate. Now we will go to the solution. Now here it is said the medium is a sphere. So we will be using this equation, equation 3. Okay, spherical del square V for a spherical coordinate system. Now coming to the solution. From the question it is clear V is a function of R only, because here it is said that is the value of V is changing according to the value of R, that is V is equal to 0 at R is equal to B and V is equal to V0 at R equal to A. That means the value of V is depending upon the radius of the sphere. So in this equation 3, this is a Laplace equation of a spherical coordinate system. You can find del square V is equal to 1 by R square dou by dou R into R square dou V by dou R plus 1 by R square sin theta dou by dou theta of sin theta into dou V dou theta plus 1 by R square sin theta dou square V by dou phi square. In this equation, the second and third term will be equal to 0. Okay, that is written here from the question. It is clear V is a function of R only. So dV by d theta and dV by d phi is equal to 0. Hence the Laplace equation for the spherical system, that is equation 3, reduces to del square V is equal to 1 by R square dou by dou R square dou V by dou R is equal to 0. That implies from this expression, if I am taking R square to the right hand side, I can write dou by dou R into R square dou V by dou R is equal to 0. Now I am integrating this equation. So I can write, when I integrate this equation, I can write R square dou V by dou R is equal to A. When I integrate this one, this dou by dou R will be removed and the right hand side is integral of 0. So integral of 0 is a constant. So I can write R square dou V by dou R is equal to A, where A is a constant. From that I can write dou V by dou R is equal to A by R square. Again I am integrating this equation. When I integrate dou V by dou R, I will get V. And when I integrate A by R square, I will get minus A by R plus a constant, right? That is equation number 6. Now, in the equation, in the question it is given the boundary conditions are V is equal to V0 at R equal to A and V is equal to 0 at R equal to B. It is given in the question. Now I am applying this condition in equation 6. So I can write V0 is equal to minus A by small a, okay, plus B that is equation 7. And next I am applying this condition on equation 6, that is 0 is equal to minus a by small b plus b, that is equation 8. I am applying these two boundary condition in equation 6. When v becomes v0, then r becomes small a. When b becomes 0, r becomes small b, that's all. So that is equation 7 and 8. Then I am minusing 7 and 8. So I will get v0 is equal to a into 1 by b minus 1 by a. From that I can find what is capital A. It is equal to v0 by 1 by b minus 1 by a. That is my equation 9. Now the next step what I am going to do is I am going to substitute this a in equation 8 to find the value of b. So I will get b is equal to v0 by b into 1 by b minus 1 by e. Okay. So that is my equation 10. Now in the next step what I am going to do is I am going to substitute the value of a and b in our main equation 6. That is substitute 9 and 10 in 6. 6 is this, v is equal to minus a by r plus b. In this equation I am going to substitute the value of a and b. So when I substitute it, I will finally get v is equal to v0 by 1 by b minus 1 by a, the whole into 1 by b minus 1 by r, which is equation 11. Now for a spherical system, del v is equal to dou v by dou r ar plus 1 by r dou v dou theta a theta plus 1 by r sin theta dou v dou phi a phi. And as I said earlier, the second and third term will be equal to 0, because in the question it is given the value of v is varying only with respect to r. So finally I can write del v is equal to dou v by dou r into unit vector ar. And we know the relation connecting E and del v. What is it? E is equal to minus del v, which is equal to minus dou v by dou r of ar. Now I am substituting equation 11 in 12. Here we have the value of v, that is substituted in equation 12. That is E is equal to minus del v is equal to minus dou by dou r of, here in place of v we will substitute this value. Okay, that is substituted. It is differentiated, and finally I will get E is equal to minus del v is equal to minus v0 by 1 by b minus 1 by a into minus 1 by r square. So minus and minus becomes 1. So finally I will get E is equal to v0 by 1 by b minus 1 by a r square into the unit vector ar, that much volt per meter. So that is the expression for electric field intensity of a sphere using Laplace equation. Now if you know E, you can find out D. What is it? D is equal to epsilon E. Using that relation, you can find out D is equal to epsilon E. D is equal to epsilon 0 V0 by 1 by B minus 1 by A R square AR, that much coulomb per meter square. Now here there will be charge density rho s only at R is equal to A. Now it is said in the question that this sphere is having a voltage at R equal, is not having a voltage at R equal to B, and it is having a voltage only at R equal to A. That means this sphere will be having a charge density only at a radial distance of A. At a radial distance of B, this charge will not be having a charge density because there V is equal to 0. So here we can say that the charge density rho s is equal to D at R is equal to E. So I can substitute in the place of R I can substitute A. So finally rho s is equal to epsilon V0 by 1 by B minus 1 by A into A square, that much coulomb per meter square. Hope it is clear. That is, at V is equal to 0 we are not having any charge density. At V is equal to V0 we are having a charge density, and at that point R is equal to A. So in order to find the charge density, it is enough to substitute A in this expression. Similarly, you can find out the capacitance also. We know there is a relation connecting Q, C and B, that is Q is equal to CV. From that you can find out C is equal to Q by V. As per this equation, that is equal to Q by V0, and this Q can be represented in terms of charge density. You have already studied the surface charge density is equal to charge per unit area, right? So charge can be written as surface charge density into area by, the denominator here is V0, so V0 is written here. So instead of Q I have written charge density into area based on the relation rho s is equal to Q by A. Okay. Now this is a sphere, and you know the area of the sphere is 4 pi r square, that is equal to rho s into 4 pi r square by V0. And in the question it is given that we are having a voltage only at R is equal to A. So I can substitute A instead of R, and finally I can write down the expression for capacitance as C is equal to rho s into 4 pi A square by V0, that much farad. And these are the two equations of del V for Cartesian system and cylindrical system that you can by heart. And that's all. Thank you.